Thank you. Okay, this is working. Yeah, so I'm Dan. I want you to interrupt me as much as possible, okay? And if we get sidetracked onto other things, that's absolutely fine. Um, and I'll confess that I haven't written all the lectures yet. So that also means that if we move in some other direction, that's, also possible. Okay, so supergravity is like a big and old subject. It's like very beautiful. There's lots of different ways we could talk about it. I thought what I would try and do is to tell you, well, no, actually, before I go there, let me try and understand what you all know. So, who's had a general relativity course? Okay. Who's had a supersymmetry course? Someone, everyone. Who's had a supergravity course? Okay, right, you can. Okay. All right, that's really helpful. So there's lots of different approaches to supergravity, and there's all sorts of like incredibly, we should be very grateful to a bunch of people who did incredibly complicated calculations to show that these theories were actually supersymmetric, right? I'm not going to do that because that's going to be some whole load of algebra and an awful lot of places I'm just going to tell you, believe me that this theory is supersymmetric. But what I will try and do is give you something that's sort of a bit more practical. So I'll try and give you things that I think you might be useful in your research. So some bits become a little list of things, but I hope along the way I'll try and tell you interesting things at the same time. So I'm going to start off just by doing some, what else should I say? Yes, so we'll talk a little bit about supersymmetry and background. Then we'll talk a bit about supergravity theories and just some simple supergravity theories. And I'll then try and give you a little bit of a list of different supergravity theories, different dimensions and what structures they have. And then if we have time, we'll then move on to some supersymmetric backgrounds, which is often what you actually use supergravity for in string theory. Or I won't really talk much about quantum theories. It's all going to be a bit classical, but think of it as effective theories, right? Low energy effective theories. So roughly speaking, so today I'm mostly going to talk about some introduction. And if my handwriting is bad or too small, please tell me. So what are the lectures? So we'll try and be fairly pragmatic. And there's going to be a focus on geometry. So, supergravity is local supersymmetry. It's necessarily got gravity in it. So everything we're going to do is gravity. Everything about gravity is geometry. So we're going to have to talk about geometry. So the framework roughly will be, so we'll start with some intro, where I'm going to tell you about Susie and some other things. And then I'm going to do a little bit of mathematics. I'm going to do some geometry. And I'm going to tell you about things called G structures. Yeah. I was waiting to see how long you could bear it for. I'm going to talk about something called G structures. And this is a kind of nice way of talking about geometry that's going to appear in lots of places through the lectures. Then I'll talk about some simple supergravities. So sugra for supergravity. I'm not sure if I like that or not, but everyone uses sugra, so I'll say sugra. And we'll look at d equals 4. It's still doing it, isn't it? And d equals 11. Then I'll tell you about the d equals 4 theory, n equal 1. That's the smallest amount of supersymmetry you can have in 4 dimensions coupled to matter. So that's sort of the most standard supergravity you might think about in 4 dimensions. Then, I'm not sure I'm going to do all this, but anyway, then we'll talk about supergravities in diverse dimension. So it's sort of going to be a list of all the different supergravities you might come across. And then it starts, then we'll talk about supergravity background, supersymmetric backgrounds. That's particular geometries, solutions of the supergravity theories that preserve some number of supersymmetries. So it's like having a background that's translationally invariant or something, right? This is now something that has a supersymmetry. And then if we have time, we might talk a bit about supergravity and extended geometries, which is my own pet obsession about how to think about these backgrounds. Okay, so that's the rough idea. I'm not sure how far we'll get through. Supergravity and what I call extended geometry. So it's a way of, geometrical way of thinking about these supersymmetric backgrounds. Yep. Any other questions? Okay. All right, so let's start. So let me start by being really simple. And let's just think about some things I think you all know. So let's think about symmetries, Hilbert spaces, and particles. So recall if you have a symmetry of a quantum theory, what do you have? So you have a Hilbert space, which I'll call H, and you have some unitary representation of the symmetry group. So that's some map, let me call it rho, which is some map from the group into unitary operators on the Hilbert space. So if this was a finite dimensional Hilbert space, these would just be unitary matrices. This might be an infinite dimensional Hilbert space, and then it's some unitary operators. And I'm not going to worry too much about the exact definitions in that case. Okay. And as you know, why unitary? Well, you really need to preserve norms, right? So what I need is like the norm of rho of A acting on a state psi overlapped with rho of A acting on a state chi. Well, this is going to be psi rho of A dagger, rho of A, chi. And this better be equal to psi chi, so that the probabilities of things are preserved when I make the transformation, right? I have the probability of something happening. If I translate my whole system and I do the same thing again, I should get the same probability. So this tells you that you need this thing to be 1, so these need to be unitary representations. I assume you've seen this before. Yeah. Excellent. You read my notes. So the next question, there's 2 caveats. Okay. So the first one is that, just as was mentioned, you can actually have projective representations. Right? In quantum mechanics, the overall phase doesn't matter. So actually, so this is like sort of up to phase, right? That's the idea. So you can actually have a representation where when you multiply the 2 matrices together, it doesn't quite come back to the representation of the product of the A and B elements of the group, right? So if I do B and then I do A, I should be that's represented by the thing that represents BA. But now it can come back up to a phase that can depend on those 2 things. That's a projective representation. That sounds like it could get a bit complicated, right? Because how do I deal with these phases? But there's a nice theorem. You can tell I can't help myself by getting sidetracked already. But there's a nice theorem which says that there's some what's called a central extension of G. So that's just think of it as some other group where you can map elements of G tilde into G, such that projective reps of G are in one-to-one with linear reps of G tilde. So you don't actually have to, you can still work with nice ordinary linear representations that you're used to, unitary representations, just by changing the group from G to G tilde. So you know this already, right? The rotation group. When you do the rotation group is SO3. When you do its representations, you do SU2, and you have half spin. The half spin representations are not a representation of SO3, they're a representation of SU2, and like if I was more agile, I could do something where I do this and you rotate twice and come back to yourself. But that's just this. This group would be, this could be the SO3 group, and this would be the SU2 group, right? Yeah.
Is there any restrictions on when this holds?
It always holds. Yep. And then there's another slight caveat.
Sorry.
Yeah?
Do you mean the phase can be absorbed as scalings of the generic?
So no, what you do is you slightly enlarge the group, sort of by something that looks like a bit like a U1 factor, which absorbs this phase so that it becomes an honest representation without any extra phase. That's the idea of the extension. Yep. And then you look at representations of that larger group, but they're in one-to-one with the projective. Yeah, yep. No, it's not always the universal cover. No. Yep.
Okay, the same question. I thought it was only the universal cover because this is the Batman theorem, right? If I'm not mistaken. And then if I'm not wrong, it tells you about the universal cover.
I think so. You don't always make a projective extension. The central extension is not always by the whole center. So sometimes it's not the whole universal cover. Yep. Okay, the other caveat is that you could have anti-unitary representations if you have time reversal. So I really wanted to stop here, right? But I sort of felt I should mention the other two things. Okay, so where am I really going? What I really want to do is to do this beautiful theorem of Wigner that you know, which is about representations of the Poincaré group. So what I really want to talk about now is representations of the Poincaré group and Wigner's classification. So if you're interested in special relativity, you know the symmetries of space-time, you're interested in quantum mechanics, so what you're interested in ultimately is what are all the unitary representations of the Poincaré group on a Hilbert space, right? If you know that, you know all the ways you could write down relativistic quantum theories. So the question is, what are all the unitary reps of the Poincaré group? And just to remind you, what am I talking about? Well, I'm talking about symmetries of Minkowski space, where I have Lorentz transformations, and I have translations. So this is really just saying, i.e., how can you do relativistic quantum theories. Any relativistic quantum theory will have to have one of these representations. So, okay, let's be slow. So let me just remind you. Let me remind you of the Lie algebra. So this group of symmetries is called the Poincare group. Let me remind you of the corresponding Lie algebra. So we have PM, which generates translations. And we have M and P, which generate Lorentz transformations. And we have an algebra where the translations commute. The Lorentz transformations just transform the momenta. So here eta Mn is looking like minus 1, 1, 1, 1. It's my metric. And then I have the commutator of the Lorentz transformations. Q, M, Q, Pn minus eta and P, MQM plus eta and Q, MPn. Okay. Probably familiar. I'm just giving you time to think about something else while I write it on the board. Okay, so and what we're actually going to be interested in, so we can actually focus on, okay, so I'll write it like this. SO31, that's Lorentz. I, that's inhomogeneous, that means I put the translations in. S means determinant 1, plus means I don't have no time reversal, right? So this is the orthochronous. So no time reversal or parity, or sorry, reflections. Okay. So this beautiful theorem of Wigner, who tells you what all the unitary representations are. And it does it by something called induced representations, but it doesn't really matter. This group is non-compact, right? Because you can boost as much as you want, or you can translate as much as you want. So if you have a non-compact group, its representations cannot be on finite dimensional Hilbert spaces, because you're trying to represent a non-compact group in a unitary group, but a unitary group is compact, so you can't represent something non-compact in something compact. So these things necessarily become infinite dimensional Hilbert spaces, right? And what you find is the following. So you basically find that the representations of the irreps of this, the irrep Hilbert space is in one-to-one with positive energy solutions, positive energy complex solutions of relativistic wave equations. Okay, so what I mean is there, if I look at all the positive energy solutions of a relativistic wave equation, that's a Hilbert space. I can add them together, right? I can multiply them by complex numbers, and I have a norm on it, which is sort of I take psi star bar psi and integrate it over the space if it's nice and if it's the support is compact somehow. Okay, so this is a Hilbert space. Okay, you've probably seen that before. This is like this is super profound, right? You should be really blown away by this because this is what we mean by particles, right? A particle is a solution of a relativistic wave equation. So this says that the only way to do relativistic quantum theory is by using particles. You had to get particles, whatever you do. So, if you go do some complicated quantum field theory, you're not really thinking about particles. You had to get particles out in the end because those are the only irreducible representations, right? So the moment you just have the symmetry and quantum mechanics, then you know you have particles. So just to say slightly more, so there's actually one, there's of course the trivial representation. So that's, you just represent everything by a single, all the operators are trivial. There the Hilbert space is just it's just one-dimensional, right? It's just isomorphic to C. And it's just complex numbers times some basis state. This is just the ground state. So there's a sort of stupid representation, which is just the ground state of the theory. And then there are massive representations. So they have some mass squared positive and some spin S, which is an SU2 rep. And SU2 is coming out precisely because we want these projective ones, right? I really want projective representations of this, and that's why instead of SO3, I get SU2. Anyway, so these are things that you know. So there's the Klein-Gordon equation. That's for S equals 0. Where am I going to go? There's the Dirac equation. That's for S equals a half. There's the Procker equation, which looks like dm an minus dn an minus m squared an equals 0. That's for spin 1. That's the Procker. This is Dirac. And so on. Right, that's an excellent question. So can I just leave that for a second and come back to it? Yeah. All right, so that's the massive ones. There's also a bunch of massless reps, which have m squared equals 0. And these actually just have helicity states, alpha. So, you could have 0 plus or minus a half, plus or minus 1, and so on. And they're like the massless Klein-Gordon, the massless Dirac, and here this mass goes to 0, and it's just electromagnetism, right? It's just the gauge theory. There are two other sets. There are some tachyonic solutions. So those have negative mass. So they're allowed, but physically we don't see them. And there's also another set which are called continuous spin, which have mass equal to 0, but they have some other parameter, I'll call it t squared, some other number which is continuous. So, and they don't have, unlike the spin representations, which have a finite number of states in them, these things have, for a given t squared, you get an infinite number of states. It's more like momentum. So these are kind of weird. We also don't see them. I'll come back and talk about them in a second. Okay, so let me make a couple of asides. So one was this question about probabilistic interpretations. So and then I'll come back to actually talking about the spin 3 halves representation, which is the one that we're going to be interested in for supergravity. Okay, so all the wave equations satisfy d squared minus m squared on psi is 0. So irrespective of which equation you have, you can always ultimately get, it always implies this. So the components, I will try. Keep reminding me, all right? Yeah. All right, so they're all going to satisfy something like the Klein-Gordon equation. And you know that if you, remember we're also requiring positive frequency, so positive energy. So if you take irreducible representations, because I don't have the time reversal, I can just restrict to the positive energy solutions, and the Poincare group will keep me in the positive energy ones. So that's an irreducible thing. But I think you probably know this basic problem, right? So if I have some psi of x, and I write my time direction in this direction, and my spatial directions here, and this is the light cone. If I start with a function here, which is localized inside the light cone, if I keep only positive frequencies, at some later time, it can have, this can be non-zero. So it can have a little bit of probability that leaks outside the light cone. So one way of saying about the problem of interpreting the Klein-Gordon equation, or actually of interpreting any of these equations if you restrict to only positive frequencies, positive energies, is that they always have some probability of sort of something propagating faster than the speed of light outside the light cone. So that's the problem with interpreting these things. So there's a problem of interpreting as wave functions. Right? If I really think of this as a function of position, that's problematic. But you know, when you do quantum field theory, I told you that these are the only Hilbert spaces you can get. These are the only things that are representations. So when you do quantum field theory, you get the same set of Hilbert spaces. You get tensor products of them, but you get the same set of Hilbert spaces. So what's going on? Quantum field theory is perfectly local. It's not a problem, right? So just to say, so if we did for so what gives? So for example, if we're doing quantum field theory, we're going to have a Fock space, which is going to look like the vacuum plus maybe some single particle Hilbert space, right, of mass m squared, let's say spin 0, plus some symmetric product of a pair of them, 2 particle states, plus etc., right? And we talk about this as single particle, 2 particle, and so on. So what's going on? Well, if I take a state here, it's one of these solutions, but let me write it not as a function of, let me just change variable, let me call it Q, so you don't think of it as being a position. And if you try and think about the field here, this is not really telling you about the position of something, it's really telling you about the first excitation of the fields and some superposition of the first excitation of the fields. So you should not interpret this variable as being like the position of something, you should interpret it as telling you something about the amplitude of the field, quantum mechanically. And when you do that, the field is perfectly local, right? So if we restrict this, we can almost think of it as like a single particle, but when you start running into these problems, you have to remember to yourself that you're really talking about a field, and that's how field theory gets around the problem. Okay? Did that help the question? Maybe. You can.
You said fields. In my mind, state, like wave function and fields are two different concepts, right?
Yep.
So I'm not.
So all I'm saying is that a given state in this one particle Hilbert space can always be represented by a function, because that one particle Hilbert space is a space of functions. And you're tempted to say, let me think of this function as a function of position, and then I'm trying to do a single particle relativistic quantum mechanics, and I have all the problems. When I interpret it as a function of something in the field theory, the thing it's a function of is not really position. It's really some superposition of the first excitation. It's to do with the amplitude of the field, right? This thing is built out of single excitations of each mode of the field. So you can still think of it as a function, but the thing it's a function of is not the position of anything. Because there is position observable, but there's a sort of, well, I mean, yeah, there's no position of a single particle as an observable. Yeah, yeah.
So what's this notation of S2 and
This thing, I just mean symmetric products. So like you symmetrize. Sorry, I should have said. So like, yeah, in the Fock space, right, you can exchange the particles and it's the same thing. Yep. Uh-huh.
So if I have an interactive theory, I still assume that I can write as a superposition of solution now expanding modes right? Or is like more complicated?
So usually in the field theory, if you assume you have some kind of mass gap, then you still have single part. You assume, so roughly you assume that the full Hilbert space is still the same as the Fock space of the free theory, but you can no longer simply interpret. So there'll be nice eigenstates of momentum, and there'll be some which are eigenstates for single particles, but then you'll hit some threshold for the two-particle state, and then the eigenstates don't nicely correspond to combinations of particles. I'm not sure if I'm answering your question. Is that all right? Yeah, okay. All right, so let me make my second aside. So what about these continuous, well, let me just say something else. So roughly speaking, if we have some non-compact group, non-compact symmetry, then the Hilbert space is going to be infinite dimensional. And it's roughly, not always, but roughly you can think of it as the space of solutions of some wave equation. So that's what we saw happened in the Poincaré case. More generally, for many non-compact groups, the same kind of thing happens. So if you think about this sort of abstractly, whereas if you have a compact symmetry, H is finite dimensional, or can be finite dimensional, And this is more like, you need to specify some, this is like specifying charges of something. So I need to specify the charge of the things in the state under the symmetry. So from some point of view, you can think of as the first case, this is like space-time. And these are like the charges, and this is like some. Sorry. So this is more like charges and some internal symmetry. So what I'm trying to say is, suppose someone be the most obscure theorist you could possibly be. Don't know what the universe looks like. Someone just gives you a symmetry group, and you look at its representations. Part of the symmetry group might be non-compact. Part of it will be compact. The non-compact bit is going to tell you something about what space-time you're in. The compact bit is going to tell you something about what internal symmetries you have. So, for example, if I went to SO 32, so what do I want to do? Then I'm going to get wave equations on ADS space. And I'm going to start seeing like, so again, by going from the inhomogeneous Poincare group, from the Poincare group to SO32, it's like changing my space-time, right? And that gives you actually a way of interpreting these continuous spin representations. So actually the continuous spin representations the continuous spin representations sort of correspond to wave equations in a six-dimensional spacetime. So their continuous parameter is like having an extra 2 dimensions. So if we'd seen them, we'd sort of be seeing some 6-dimensional spacetime rather than some 4-dimensional spacetime. So that's one way of thinking why we don't see that's sort of how we don't see the continuous spin ones. It's not a simple spacetime. It's not just Minkowski with 2 extra dimensions on it. Okay. But let me go back to what we really want to do, which is, yep, this bit. Okay, so I sort of glossed over. So the continuous spin had m squared equals 0. And you got some wave function, which is a function of position. And then there are 2 extra continuous spin variables, which are a bit like 2 extra momenta. And I can think of them as having another set of variables, another 2 coordinates. So if I did a Fourier expansion, I would have, the ordinary expansion of this in terms of momenta, and then I get 2 more expansions from this, which is the extra continuous spin variables. So you can actually write down a wave equation in 6 dimensions, which gives you the solutions of which correspond to the continuous spin representations. Is that okay? Any more questions? Okay. But I'm getting sidetracked. So what I really want to talk about is let's do, in the classification, we had a spin 3/2 massless. So what wave equation does that look like? So it's actually the following wave equation. So the field is something which is a spinner, but it also has a vector index. So it's got a spinner index and a vector index on it. And that makes sense because the vector is like spin 1, the spinner is like spin 1/2, so it's in the tensor product of spin 1 and spin 1/2. Is that okay? And what wave equation does it have? Well, if I do the massless one, I can write the wave equation in the following way. So let me explain a little bit what I'm doing. So this is called the Rarita-Schwinger equation. And I've got gamma matrices here, so I've got some gamma m, gamma n, plus gamma n, gamma m is 2 eta mn times 1. And then by this thing, when I write gamma m1 through mr, I mean 1 on r factorial times the sum over the permutations times the sign of the permutation, and then I write gamma m1, gamma m2 through gamma mr. So I'm permuting these indices around. So it's just like the anti-symmetrization of that thing. So I had this thing with 3 indices here. Okay, so this is what properties does this equation have? Well, interestingly, it has a local symmetry. In the same way that like a gauge field has a local symmetry, U1 gauge field has a local symmetry, I can take this psi m field and I can send it to psi m plus the derivative of some spinor. So this is just some spinor. And when I do that, because this is anti-symmetrized, so then gamma mnp dn psi p goes to gamma mnp dn psi p plus dn dp epsilon, but this is just gamma mnp dn psi p, right? Because the derivative's anti-commute. So it's very like the symmetry of gauge fields. And this, so this is the sort of new symmetry by a parameter which is a spinor. And it's this kind of gauge symmetry which is going to, this is what's going to turn into local supersymmetry in supergravity. So this is like the linearized version of that. Yep.
I think it's my lack of prerequisite knowledge, but can you say a little bit more about this epsilon? Like, are we talking, like, my knowledge is maybe from more representation?
Yep.
Like, are you saying that this epsilon comes from representation, or are you thinking like valued function?
So it's in the spinor representation, and it's a function of position. Yep. So it's, if you like, it's a section of the spinor bundle over spacetime. Yeah. Which is trivial in this case. So that's just. Is that all right? So a spinor is a representation of the Clifford algebra. And I just take the same Clifford algebra at each point in space-time, and I take a spinor, which will be some just vector that some number of components which transforms into the gamma matrices, and I just let that thing depend on where I am in the space-time. Yeah. Is that, maybe I didn't say very well, but are there other questions? Okay, so if you want a little exercise, am I supposed to be giving you exercises? I'm sort of supposed to be giving you exercises. I could be giving you exercises. Okay, so here's an exercise. So with some gamma matrix manipulations, this is because it's not fair to teach you supergravity without getting you to do some gamma matrix manipulations, because that's all the complicated things you have to do when you actually do supergravity, right? Show that equation of motion that I just wrote down, this one, is equivalent to gamma m dm psi n minus dn psi m is 0. And then if you want, fix a gauge. So that's using that symmetry, which is gamma m psi m is 0. And then what's the residual symmetry? So what I'm doing is very like showing how electromagnetism only has two polarization states, right? When you look at the wave solution, the wave equations, you usually fix the Lorentz gauge, and then you try and see what's left over. There's still some residual symmetry left over, and you find that there are just two helicity states. So show there are only two independent helicity states for psi. So this is supposed to be massless spin 3 halves, right? So all massless fields just have two states. So you should sort of compare this with electromagnetism. This is a little bit of a pain, so you could just stop there. I'm not saying you should do it. Say again? I will try and, thank you. Thank you. All right, so do I just start again, or do I just start again, or do I? Yeah. Okay. All right. So I think I'm going to tell you about Clifford algebras and spin. So So we already saw some spinners, and I just assumed you knew what you were talking about in 4 dimensions. But we're going to do supergravity in lots of different dimensions. So I really need to tell you about spinners in arbitrary dimension. And I'm going to go on I'm going to be polemic about it and tell you how you should think about it, and you should never think about it any other way. Okay? So, and it's also kind of beautiful. So why don't we? So okay. So recall that spin plus 3,1 was the double cover of SO plus 3,1, and we needed its reps, and its reps are relevant for still. For projective reps of SO plus 3,1, or ultimately ISO. So we want to think about the spin groups. That's what I'm trying to say. So, so what about in general dimensions? Well, the idea is you use something called the Clifford algebra, which is really just the gamma matrix algebra. So, but let's be slightly more mathematical about it. So I'm going to write it in the following way, which is going to. So we're in. So let's write. I'll write Clifford. I've got some vector space, and I've got some quadratic form. Okay, so what do I mean? Okay, I'm going to write some things that won't mean anything, and then I'll tell you what they are. So, all right, so what do we have? So V is a vector space. And for us, it's going to be, it's just going to be RD in D dimensions. Eta is some quadratic form. So for us, it's going to be a metric, eta of signature. And let's be completely general, PQ. So I'm going to have P plus signs and Q minus signs. So we can even do spinners in 2 tie directions. And then T of V is just the tensor algebra. So that means, you know, for us, so it's going to be the reals plus the vector space plus the tensor product of the vector space with itself plus 3 tensor products plus etc. So you should think of it as like a scalar thing, a vector thing, a thing with 2 indices, a thing with 3 indices, and so on, right? And then I eta is a relation which just says that UV plus VU, so I take 2 things in the vector space, and when I take their tensor product and take them the other way around, this thing is just equal to twice times the inner product between them times the 1 that lives in here. So that's just like the gamma matrix algebra. Sorry, maybe I shouldn't have been quite so formal, but anyway. So what you're doing is you're taking a general thing that's got functions, vectors, 2 index things, 3 index things, and so on, and then you use this relation to simplify it. So how does that work? So for example, yep. This I eta? Oh, it's a relation. Sorry. Sorry, that was terrible handwriting. Okay, so let's just do an example. So suppose, so let's write, I'll write CLPQ, right, for signature, for the Clifford algebra with signature PQ. And let's just do CL20. And I can choose a basis. So I can write my vector as a scalar plus, sorry, I choose a basis, so let's say gamma 1, gamma 2, which is a basis in the vector space. Okay? So a general vector now I can write as v1 gamma 1 plus v2 gamma 2. I guess I want to, maybe I want to write these down. Actually, sorry, let me get my indices in the right place. Let me write these down. Doesn't really matter, but just so I have it. Okay, so if I think about a general element of the Clifford algebra, it's going to look something like, well, it's going to have a scalar part. It's going to have a vector part. And then it's going to have things where I take the product of two things, but there's only really one thing I can do there, which is gamma 1, gamma 2, because I find that, right, from here I have that gamma 1 squared is 1, gamma 2 squared is 1, and gamma 1, gamma 2 is equal to minus gamma 2, gamma 1. And so it stops, right? There's nothing higher, because using that relation I don't get anything higher. And I also notice that if I take the product gamma 1, gamma 2, and I square it, this is gamma 1, gamma 2, gamma 1, gamma 2. That's the same thing as minus gamma 1, gamma 1, gamma 2, gamma 2, which is the same thing as minus 1. So I have two things that square to 1, and I have something else that squares to minus 1. Okay, did I do that too quickly? Do you see what I'm doing? Yep. Okay. But you notice you should compare this with the matrix algebra. Let's call it of 2 by 2 real matrices. So that has elements which I could write as A plus V1, I hope I get this right, V2 plus B, V2 minus B, and A minus V1. Or equivalently, as A times 1, 0, 0, 1, plus V1 times 1, 0, 0, minus 1, plus V2 times 0, 1, 1, 0, plus B times 0, 1, minus 1. And hopefully, you will see that these matrices, gamma 1, gamma 2, gamma 1, 2, satisfy the same relations. So you see that actually this is isomorphic to the Clifford algebra 2, 0. So we define these abstract things that are built out of gamma matrices. In a simple case, we find that it's isomorphic to some matrix algebra. Matrix algebra, I can add matrices, I can multiply them together, so I get a nice matrix. Now you can keep doing this. So let's do another example. So if we did the Clifford algebra 0, 2, I'd again have an element that looks like A plus V1 gamma 1 plus V2 gamma 2 plus B gamma 1 gamma 2. And again, I have gamma 1 gamma 2 equals minus gamma 2 gamma 1 equals a half gamma 1 gamma 2 minus gamma 2 gamma 1, which is what we call gamma 1 2, right? So sometimes I could write it like that. It's the anti-symmetrized thing. But now we have that gamma 1 squared is equal to gamma 2 squared is equal to gamma 1 gamma 2 squared is equal to minus 1. But this you should be compare with the quaternions. So I don't know if you've seen the quaternions before or not. Some people probably haven't. I'm going to assume you haven't totally. Okay. So this is like the quaternion. So what do I mean by that? That's a number. Let me call it Q, which is A times A plus V1 times I plus V2 times J plus B times K. So the idea, you're used to complex numbers where you extend the real numbers by I, where I is the square root of minus 1. You might have asked if you were a mathematician, you might ask yourself, are there other ways I could extend numbers so that I still get a sensible algebra? That's a division algebra. That's somewhere where you can do addition, subtraction, multiplication, and division. And it turns out that there are basically only 4 ways of doing that. You can do the real numbers, you can do the complex numbers, you can do the quaternions, which is where you just add in another, so we again have I squared is minus 1, but these other j and k are also minus 1. So it's like you've got 3 different imaginary directions. And then you have the relation that I times j is minus j times I is k, and cyclic. So you know, j times k is I, and k times I is j, and so on, right? So those things are called the quaternions. They're usually represented by an H for Hamilton, who's the person who wrote them down. I think he has them on his grave. I believe that's the correct statement. And there's one other set which are called the octonions. And interestingly, what happens is the quaternions, right, are not commutative anymore because ij is not the same as ji. The octonions, as you might guess, you have 7 of these things of the ijk's. So the whole thing has 8 numbers in it instead of 4 numbers, real numbers in it. And they drop associativity. So that's really wild. Just to say as an aside, the classical Lie groups, right? You're used to the classical Lie groups, the ones you can classify using as simple, you know, but the compact ones or the simple Lie groups. So you're used to there being special orthogonal and special unitary. So these are matrices, these are real matrices that preserve a norm. These are complex matrices that preserve a norm. There's also like the symplectic group, which you should really think of as quaternionic valued matrices that preserve a norm. And then you're wanting to have something which are octonion valued matrices that preserve a norm, but that doesn't make any sense because the numbers are not associative and groups are supposed to be associative. But you know that there's a whole load of exceptional groups here, right? Like G2, F4, and E6, and right, you've heard those groups. So they're in the classification, and each of these exceptional groups you can build in some way using the octonions if you work hard enough. So in some sense, these octonions, these exceptional groups are wanting to be the symmetry group of octonions, but it doesn't quite work because they're not associative. And that's why you don't get a whole family of them, you just get a few special examples. Okay, So you can think of this algebra as the algebra of these quaternionic numbers, right? You can add them together and multiply them together, provided I use those rules. Is that okay? And then so you can do some other stupid cases. So like if we did the Clifford algebra of 0, 1, then I just have a single gamma matrix, gamma 1, that squares to -1. This is just isomorphic, and an element here looks like A plus B gamma 1. And this is going to be, so this case is isomorphic to just the complex numbers, right? It's like I just have a gamma matrix that's acting like the square root of -1. And if I do C10, now I have a gamma squared that's 1. And this thing is just isomorphic to 2 copies of the real numbers. I have just the real numbers for A, and I have the real numbers for B. There's no sense that squaring this one, you know. Okay. So now here's the magic. This happens for all the Clifford algebras. Whatever the values of P and Q are, they're always isomorphic to some matrix algebra. So let me write you a table for how it works. So the reason I'm doing this is because representations of the Clifford algebra become the spinors that we're interested in when we want to do spin. Okay? I'm going to come to that. But this works for all P and Q. So let me write down the ones that are the ones we're probably interested in. So I'm going to make a long list. So let's see how we get on. So we do C01, C11, C21, C31. I'm doing the ones that look like Minkowski spaces, right? I'm always choosing one time direction. So these are Clifford algebras. And what are they isomorphic to? So this one is C. This one is isomorphic to the matrix algebra over the reals. This one's isomorphic to 2 copies of that. This one's isomorphic to real matrices, 4x4 real matrices. Then we get 4x4 complex matrices. Then we get 4x4 quaternionic matrices. I'll keep going, just so you have the list. Then I get 4x4 quaternionic plus 4x4 quaternionic. Then I get 8-dimensional quaternionic. Then I get 16-dimensional complex. Then I get 32-dimensional real. And finally, let's go up to 11 dimensions, because you know that's the biggest dimension you can get to. And I get 32 real plus 32 real. Okay. So these things all embed inside each other. You can put the complex numbers inside 2 by 2 matrices, you can put 2 by 2 matrices inside here, you can put these inside here, and so on, right? Because they're subalgebras of each other. And if you look, there's actually a pattern that repeats with a periodicity of 8. So I go complex, real, real plus real, bigger real, complex H without changing the dimension, pair of H's, bigger H, and now here I'm back to complex, and it's like this one. And I just went up by 8. And now I go real of double the dimension, that's like this, and then I go 2 copies of real double the dimension, that's like that. So although the size of the matrices get bigger, there's something that repeats of order 8. So for completeness, because sometimes people put the time in the other direction, right? Sometimes people choose minus plus plus plus. Sometimes they choose plus minus minus minus. So I also really need to think about these Clifford algebras too. So let me write down this sequence as well, just to let you fall asleep. So that's R plus R. This one we already saw is 2R. This one is 2C. Oh, what am I doing? 1, 2. 1, 3 is 2H. 1, 4 is 2H plus 2H. 1, 5 is 4H. 1, 6 is 8 complex. 1, 7 is 16 complex. Oh, sorry, 16 real, that's better. 1, 8 is 16 real, 16 real. 1, 9 is 32 real. And 1, 10 is 32 complex. Okay. So if you look, you get the same sequence period at 8. And what happens is you get a sequence depending on P minus Q mod 8. So the Clifford algebras, every time you go through P minus Q mod 8, they look the same, but they might be bigger, they'll be bigger matrices. Okay? So 1, 1 is the same as 9, 1, but with bigger matrices. 0, 1 is the same as 8, 1, but with bigger matrices. Okay. All right. And notice that in a couple of cases, these things split, right? So in odd dimension, D equals P plus Q, you can construct this thing, I'll call it gamma D, which is gamma 1, gamma 2, all the way up to gamma D. And this commutes with everything. So it's in the center. And furthermore, if P minus Q is equal to 1 or is equal to 1 or 5 mod 8, then gamma d squared is equal to 1. If it's not 1 or 5 mod 8, then it squares to minus 1. And the algebra splits. So I guess I mean for odd d. So I'm still. So that's what you see, and it splits into eigenspaces of gamma d. So you can see that happening here. There's two possibilities. So it either splits into a sum of things which are quaternions or a sum of things which are reals. Okay. We are going to get there, I promise. I'm just giving you a whole lot of bits of information. So what about spin? Well, you can think of spin as the generator as being so spin PQ. You can get an element of that by like exponentiating something with a pair of gamma matrices, right? That's probably you've seen that from, right? The gamma matrices generate the spin group. So I'm just going to think of it the same thing. But if I do this, this is going to be an element of the Clifford algebra, which is even. So this is the even Clifford algebra, which lives inside the full Clifford algebra. So that's built just out of A plus B mn gamma mn plus C mn pq gamma mn pq plus. So it's only built out of even combinations of the gamma matrices. Because this thing has two gamma matrices in it, when I exponentiate, I'll only ever get an even number of gamma matrices. And the even gamma matrices close amongst themselves. If I multiply two even things, it stays even. So there's always a subalgebra of the Clifford algebra that's built out of just the even ones. Is that okay? Say again, sorry. So what I mean is the elements of the Clifford algebra, right, are something plus something times gamma matrix plus something times a pair of gamma matrices plus something times 3 gamma matrices. The even ones, I only have something times just the numbers plus something times a pair of gamma matrices plus something times 4 gamma matrices. And since even number of gamma matrices times even number of gamma matrices stays even, it's a subalgebra. Yeah. But there's a nice result, which is the even gamma matrix, the even Clifford algebra, PQ, is the same as the Clifford algebra P minus 1Q if P is greater than or equal to 1, and is equal to the Clifford algebra Q minus 1P if Q is greater than or equal to 1. And this is also isomorphic to the even Clifford algebra QP. Because you don't see the overall of the metric because you're only looking at even things. So from these big tables, I can now write down, which one shall I keep? Let's keep this one. So now I can write down the following, which is going to be the corresponding things with even. And now it doesn't matter whether I look at 0, 1, or 1, 0, because they're going to be the same. So 0, 1, that's just the reals. 1, 1 is R plus R. 2, 1 is 2R. 3, 1 is 2C. 4, 1 is 2H. 5, 1 is 2H plus 2H. How am I doing? 6, 1 is 4H. 7, 1 is 8C. 8, 1 is 16R. 9, 1 is 16R plus 16R. And 10, 1 is 32R. Okay. Yeah.
Possibly going off on a tangent.
Yep.
Heard of the where they fit into this?
Excellent. So the pin groups sit inside the full Clifford algebra. So the pin group is the group where you allow reflections and time reversal, right? As well as just the, so you're allowed reflections. But it's again the double cover of the group which has reflections in it. So actually we're interested, right, in representations of the spin group and representations of, and you might also be interested in representations of the pin group. So since spin plus PQ sits inside this even Clifford algebra, then representations of the Clifford algebra are representations of this guy, and they're actually the spin representation. And they're really obvious what they are, because we've got all these matrix algebras, so you just take the representation that's just the representation by the matrix. Okay? So you just take the representation space to be the vector space on which the matrix algebra acts. Sort of the defining representation, right? And the whole reason that I've stressed all this is not so I can write lots of tables on the board, but because you're used to people saying, I think, when you read some supergravity paper, they say, oh, well, in 7 dimensions, the spinors are symplectic Majorana, or the spinors are Majorana and Weyl. But all that's saying is, what kind of even Clifford algebra do you have? So Majorana spinors are real spinors. So whenever this algebra is real, you have Majorana spinors. So in these 3 cases, here, here, and here. So for example, 10-dimensional spinors are Majorana. If the algebra splits into 2 bits, which are eigenstates of that gamma d, then it's vial. You're splitting it into two chiralities. So these are vial, these are vial, these is vial, right? So you see that in 10 dimensions, there are spinors which are both Majorana and vial, because you could take the spinors to just be a representation of that bit or of that bit. It would still be a good representation, right? So if the matrix algebra is real, that corresponds to Majorana spinors. So you see here, the spinors are 16-dimensional, right? Because these matrices act on a 16-dimensional thing. So the spinor is 16-dimensional, and it's Majorana vial. If the matrix algebra splits, that corresponds to a vial spinor. And if the matrix algebra is quaternionic, that corresponds to what's usually called a symplectic Majorana condition. Okay? And I'll say a little bit about that in a moment. So what people often do is they think about the Clifford algebras over the complex numbers, and then they start putting reality conditions on and stuff. But when you're doing supersymmetry, or supergravity theories, you're really doing classical theories and everything's over the reals. So it's much more natural actually to think of everything over the reals. And then you're just interested in seeing which kind of Clifford algebra, even Clifford algebra you get out, and then you can read off what kind of spinor type you have. Okay? Yeah. Sorry. These ones? So just take the representation space to be the vector space on which the matrix algebra acts. So I just mean like there's a vector that it acts there. The one above? Okay, so if the matrix, I'll try and write better, this is what I really need to do, right? If the matrix algebra is real, then we call the spinors Majorana. If the matrix algebra splits, so that's like these cases, then we call them vial spinors. And if the matrix algebra is quaternionic, we call them symplectic Majorana. So, and if you did the pin algebra, if you did the pinners, so if you wanted to put in reflections as well, so if you did pin PQ, which means you include reflections, then the pinner, this is a terrible joke, right? Spin, you take the S off, SO, sometimes it's embarrassing to be a theoretical physicist. So. Then the pinners are just the representations of the full Clifford algebra, not the even part. So then I would look at that list. So if I want the pinners, they're the things that sit there. The spinors are the ones that sit in the even thing. Any more questions? Okay, so maybe I should. Well, I said it. So yeah. Let me just say quickly about this weird symplectic Majorana thing. It would be much better if we all just thought in quaternions, right? If you were happy to think of things as being quaternions, you would never talk about symplectic Majorana. You would just say, oh, it's an algebra where everything's a quaternion. And I should think of my spinors as being things valued in the quaternions, not things valued in in complex numbers. So if I wrote down the Dirac field, I should think of it as something with quaternionic valued, right? But we're not very good at that. So instead what we do, so what is this symplectic Majorana? So we use a homomorphism. So you can think of the quaternions, you can map them, what did I call it? There's a map, let me call it chi, which maps the quaternions into 2 by 2 complex matrices. This is just the Pauli matrices. Right? I times the Pauli matrices have the same properties of the quaternions. So all I'm doing there is doing the same thing. So what I do is I take some quaternionic number, which is W plus IX plus JY plus KZ, and I map it into the matrix that looks like, I hope, W minus IZ, W plus IZ, X minus IY, minus W, oh no, sorry, plus IZ, minus IZ plus, minus X plus IY. So I'm using like I times the Pauli matrices here, right? This is like I times sigma 3, I times sigma 1, I times sigma 2. So let's call that matrix M. So we want to now think of the quaternions, these matrices over the quaternions, as instead matrices over the complex numbers, but twice as many and with twice as big matrices. But if you think about the complex conjugate here, the complex conjugate of this matrix is W minus IZ, X minus IY, minus X plus IY, and W plus IZ. And hopefully, I hope I didn't do this right, wrong, you can write this as some, let me call it D times M times D inverse, where D is the matrix 0, 1, minus 1, 0. So if I have a so if I think about some spinor, epsilon 1, epsilon 2, right? I can define another spinor, I'll call it the conjugate one, which I'm going to define as omega to the minus 1 times epsilon star, right? And if I have that epsilon maps into M times epsilon, that's how it transforms under the action of the Clifford algebra, thought of now as this little matrix. This one's going to map into omega minus 1 M epsilon star, which is the same thing as omega, sorry, not omega, D to the minus 1, same thing as D to the minus 1, D to the minus 1, D, M, D inverse epsilon star, which is the same thing as M times epsilon conjugate. So what I've shown is that these guys transform in the same representation as the original epsilons, right? The two representations are equivalent, where the intertwiner between the two equivalent representations is this thing D. Is that okay? Tell me if it isn't. So it looks like you could set a reality condition where you set epsilon c equal to epsilon. But the problem is because of this d, epsilon c c is minus epsilon. So that condition doesn't make any sense. But what you can do is introduce a pair of spinors, epsilon 1, epsilon 2, where epsilon 2 is equal to epsilon 1 conjugate. Sorry, that's terrible. I called these epsilon 1, epsilon 2. That's terrible. Let me call this AB. Okay. So these are little 2 by 2 things. So concretely, epsilon 1 is AB, and epsilon 2 is going to be, oh goodness, the inverse is, so it's going to look something like minus B star A star, I think. And then I also get that epsilon 2 conjugate is minus epsilon 1. So this is this weird Majorana-Weil condition. Sorry, this is this weird symplectic Majorana condition. I'm trying to put a real condition on this spinor. I can't, because if I take the conjugate twice, it doesn't come back to itself. So instead, I think of a pair of things that get exchanged under conjugation. Yeah. Yeah. So now we're acting with these matrices on these objects. So if the Clifford algebra was just H, right, the spinors on which it's going to act, I can think of as 2 component matrices here under this homomorphism. And now I really should just think of them as acting on the quaternions, and you're done. But people don't like that. They want to think of it as acting on 2 component things, and then they want to try and put a reality condition on those 2 component things. But you can't. It doesn't quite work because of this extra minus sign. So instead, you introduce a pair of objects. So what we have is that epsilon I conjugate is omega ij epsilon j, where omega ij is, see if I can get it right, 1 conjugate is 2, so 1, and I introduce this pair. So this symplectic Majorana is that whenever you have a quaternionic thing, instead of thinking of it as a quaternionic thing, you think of it as a pair of complex things that are related to each other by complex conjugation. It's a very complicated way of doing it, but that's the way people do it, because you don't want to think about quaternions. Yeah. Yes. Yes, so epsilon c is its conjugate. It's the, I take the complex conjugate, so this thing would be A star B star, and then I multiply it by this matrix D, which is this. And now I introduce another 2 component spinor. So epsilon 1 I call epsilon, that 2 component spinor, and epsilon 2 I call the conjugate thing. Sorry, I did it very badly. Epsilon 2 is the conjugate. So for each quaternion, I introduce a pair of complex spinors that are related to each other by conjugation. That's what this symplectic Majorana condition is.
Is it an accident that E and omega are the same?
It was kind of an accident of the way I represented things, but it's not totally an accident. They both have to square to -1. D squares to -1, and also this omega thing squares to -1. Okay, I know that was a little bit painful, but I wanted to make sure you at least knew what the terms meant when they appear. Are there questions? Okay, why don't we stop there, and then I'll see you tomorrow.